How are you, learner? Welcome to our physics lesson. My name is Purity Anzelimo, and in our lesson today, we continue with topic in Form 2, that is Waves 1. We continue with the Waves 1. In our previous lesson, we introduced the topic. We were able to define a wave. Later on, we looked at the classification of waves, where we looked at the two major types of waves, that is electromagnetic waves and the mechanical waves. Do you recall what are electromagnetic waves? We said that these are waves that do not require material medium for their transmission. What about mechanical waves? For mechanical waves, they require a material medium for their transmission. And therefore, in our lesson today, we now look at waves are further divided into two, that is transverse and longitudinal. So we are still in classification of waves, and we are saying that waves are further divided into A, transverse waves, and B, longitudinal waves. And so in this lesson, we'll be discussing transverse waves and longitudinal waves. So by the end of the lesson, you should be in a position to define the two, giving examples. So we'll start with the first one here, that is the transverse waves. So we need to know what are transverse waves, examples of transverse waves, and we can also explain more on those transverse waves. Then we are going to look at the longitudinal waves. Now, what are transverse waves? When we talk of transverse waves, we simply refer to waves whose vibration of particles is at right angle to the direction of wave. Or we can simply say that transverse waves are waves. So make note of this, that transverse waves are waves whose vibration of particles is at right angle to the direction of wave travel. And I'll be explaining this more. So transverse waves, we are saying they are waves whose vibration of particles is at right angle to the direction of the wave travel. So here we are talking of at an angle of 90 degrees. So we can start first by giving examples, then we'll explain this more, what we are talking about when we say that the vibration of particles is at right angle to the direction of wave travel. So we can first give examples of transverse waves. We are going to start with all electromagnetic waves, because we say that all electromagnetic waves are transverse in nature. So we list them down first, all the electromagnetic waves. So we have listed down the electromagnetic waves, the radio waves, the X-rays, the microwaves, the radiant heat, the light waves, gamma rays. We also have the radio waves. So these are the electromagnetic waves. In addition to that, we also have what we refer to as the water waves. Water waves are examples of transverse waves. We also have waves on a rope. Waves on a rope, on a slinky rope. They are also examples of transverse waves. So these are examples. So when you are told to give examples of transverse waves, we have listed down so many of them, because the first part is on electromagnetic waves, whereby we have seen all the electromagnetic waves are transverse in nature. We have also added the water waves, they are transverse. We also have waves on a rope. And I want us to consider the following. Consider the following. Here I want us to consider a rope which is fixed on one side. This is a fixed end. And then we have a hand which is moving the rope up, down, up, down. So we have the hand moving the rope up, down, up, down, up, down, up, down, up, down. So here is the hand which is holding the rope. This is the hand movement. That is what we have, and we can see that the hand movement repeated regularly. So we have the hand moving up, down, and this is now the wave, and this is what is going to be portrayed. So this is what we have. And we have seen that an example of a transverse wave is a wave or waves on a rope. That is what we are seeing here. So on one end we have a fixed end. I'm sure you have done this, especially when you are playing, especially when you are young. So now this is an example. This is a transverse wave. You can see there are some sections which are at this point, others at a higher point. Lower point, higher point. So they alternate. A higher point, a lower point, a higher point, a lower point, alternating each other. Now this point, the higher point, is referred to as the crest. It is called the crest. This is the crest. Then the lower part here is called the trough. So we can say in a transverse wave, we have crest, trough, crest, trough, crest, trough, crest, trough. So we have series of crests alternating with troughs. So that is very key, that in transverse waves, so we are saying that transverse waves have series of crests alternating with troughs. So you find a crest, a trough, a crest, a trough, a crest, a trough. So when you are given a wave, for example, if a wave is drawn like this one here, a wave is drawn, and you are told to classify this wave. So by just looking at it, you can see there are sections of crest and troughs, and therefore you can classify this wave as a transverse wave. You can be told to classify a wave, so that is a transverse wave. It has series of crests alternating with troughs. So that is what we are referring to as a transverse wave. And for an individual particle, for an individual particle, we are going to have it this way. So if we have our particle here, and the particle displacement up, down, have it, this is the particle displacement. And we are saying that we are moving it in this direction. So this is the wave motion. This is the wave motion. Because we are saying you are moving the hand in a repeated movement, up, down, and we can see that the wave moving in this direction as the particle moves up and down. and therefore we are saying that this is an angle of 90 degrees, and that find a transverse wave as a wave whose vibration of particles right angle to the direction of wave travel. So that is what we are referring to as transverse waves. So that is all for now on transverse waves. We are saying that there are waves whose vibration of particles is at right angle or it is perpendicular to the direction of wave travel. And we have listed down the examples of the transverse waves. Then we went ahead and said that transverse waves have sections, or they have series of crests alternating with troughs. So we have the upper section as a crest and the lower one as the trough. And we are also saying that for an individual particle, this is what is going to be formed. So there we are saying that the vibration of this particle is at right angle to the direction of the wave travel. Hoping that that is clear for the transverse waves. So we move ahead and now look at longitudinal waves. So we have B, we have longitudinal waves. We need to start by defining longitudinal waves, then giving examples of longitudinal waves. Now when we talk of a longitudinal wave, it is a wave whose vibration of particles is parallel to the direction of wave travel. So that's what we are referring to as a longitudinal wave. The waves, that is longitudinal waves, are waves whose vibration of particles is parallel to the direction of wave travel. So you can see the difference between the longitudinal and the transverse waves is the direction. So for the longitudinal waves, the vibration of particles is parallel to the direction of wave travel. And an example of a longitudinal wave, we have one, maybe you can research for others. An example of a longitudinal wave is what we call the sound waves. Sound waves. They are examples of longitudinal waves. Remember, we had seen that sound wave is a mechanical wave, and we said for mechanical waves, they can either be transverse or longitudinal. So one of the waves that is in mechanical waves, that is the sound waves, is an example of a longitudinal wave. So it's a wave whose vibration of particles is parallel to the direction of wave travel. And an example is the sound waves. And I want us to consider the following to understand better on longitudinal waves. Now here we are going to consider a spiral spring. We know that a spiral spring is able to stretch, and also we are able to compress it. So if we have a fixed end here of the spring, then on the other end, so we have the spring fixed on one end, then on the other end, the hand is able to pull, compress, pull, compress. So we have it in this direction. So we are going to have our spring as follows. So we have some sections whereby the spring will be very close to each other, and some other points where the spring is far away from each other. Here it is closer, far away from each other, closer again, and so on. So on this side we are having the hand which is making this movement. Here we have the hand, and the motion is a to and fro movement. This is a to and fro movement. So that is what we are going to observe in the spring. So we have some sections which are very close together. The particles are very close together. Here they are far away from each other. And this section where they are closer to each other is referred to as the compression. This is the compression. Make note of that. So it has a compression. Then we have the other areas where it is away from each other. This section is referred to as rarefaction. And note it is rarefaction, not function. It is rarefaction. So we have, for a longitudinal wave, we have sections of compression alternating with rarefaction. So we have compression, rarefaction, compression, rarefaction, compression here. So we can say that for a longitudinal wave, so now you should be able to give another difference between the longitudinal and the transverse waves. So for the longitudinal waves, they have sections of compression alternating with the rarefaction. So for the compression, it's where the spring is closer together, rarefaction far away from each other. So for an individual particle, we can explain it further. For an individual particle, if we have our particle here, we have the particle, we are going to have the particle displacement in this manner. This is our particle displacement, either that side or the other side. This is the particle displacement as the wave moves in this direction. So this is our wave motion. And therefore, this explains what we are saying, that the vibration of particles is parallel to the direction of wave travel. So we are saying if we have our particle displacement, we have seen in an example of a spring, we are moving it in a to and fro direction. So we have this particle displacement as the wave is moving in this direction. So we can say that the wave, the particle displacement, you can see it's parallel to the wave motion. And that is a longitudinal wave. So for a longitudinal wave, the vibration of particles is parallel to the direction of wave travel. And we can say that in the compression, the particles are closer together, whereas in rarefaction, we can explain that in the compression, the particles are pushed closer together, whereas in the rarefaction, particles are pushed slightly further away from each other. And this variation will be accompanied by pressure variation. So us having the particles closer here and here further away from each other, then we are going to say that the interparticle separation is accompanied by pressure variation. So the interparticle separation is accompanied by pressure variation, where we have the particles pushed closer together, there will be high pressure. So at the compression, there is high pressure. At this section of rarefaction, there is low pressure. So here there is high pressure, whereas at the section of rarefaction, there is low pressure. And it is as a result of the pressure variation that the wave is able to move. So we can say that the pressure variation causes the wave motion. The pressure variation. So it is as a result of the pressure difference between these two sections that the wave is able to move. Because we also saying that movement is as a result of pressure difference. In the topic pressure in book 1, we're saying that liquids are able to flow due to pressure difference. So we are saying because here we have a section of compression where the particles are closer to each other than in the rarefaction. As a result, this will lead to a high pressure here and a low pressure at the section of rarefaction. And we are saying that this pressure variation will cause the wave motion. So that is all for now on the longitudinal waves and the transverse waves. We have seen for transverse waves, the vibration of particles is at right angle to the direction of wave travel. We've been able to give the examples of transverse waves, and we have seen that transverse waves have sections or they have series of crests alternating with troughs. So that is on the transverse waves. Then we have explained about the longitudinal waves, whereby we have seen that longitudinal waves are waves whose vibration of particles is parallel to the direction of wave travel. And in this, we have been able to explain using a spiral spring. And we have also been able to see that for longitudinal wave, it has sections of compression alternating with rarefaction. And we have seen that it is as a result of this whereby we are going to have pressure difference between the two, and as a result of the pressure variation, there will be wave motion. So some questions on this. So here is the question. Give one example of a transverse wave and a longitudinal wave. Then in the same question, you are told to explain what is the main difference between these two types of waves. So what is the main difference between transverse and longitudinal waves? So in our next lesson, we'll now be looking at, after now we are done with the classification of waves, now we look at the characteristics of wave motion. Characteristics of wave motion. So that's where we'll also look at the terms associated with waves, very important. It will also help you in waves 2 in book 3. So till we meet next, continue revising what we've covered in the previous lesson. Thank you.